These are the notes for Chapter 19 from the McGraw-Hill text on oxidation reduction, aka redox reactions. So we're going to start out kind of like we did with acids and bases. We're going to talk about some of the theories and the groundwork for oxidation and reduction. Originally, scientists thought that oxidation was the addition of oxygen to some substance, and thus the name oxidation. And when you took oxygen away, that was a reduction in the amount of oxygen, thus the name oxidation and reduction. When we look at reactions like that, say C plus O2 yields CO2, that's an addition of oxygen. That would be called oxidation. So there's one name for the reaction. If we reverse that and we lose oxygen, that's reduction. Also, hydrogen was involved. When we talk about the addition of hydrogen, so carbon plus 2H2 yielding CH4, that was addition of hydrogen. Addition of hydrogen is just the opposite effect of oxygen. Addition of hydrogen would be reduction. So that would be a reduction, and losing hydrogen would be oxidation. You should make a little card that has those four on it, kind of flashcard, so you can help remember that. As we moved through time, we got to a point where people understood a little more about the chemistry involved, and like many other things, the electron is the culprit here. So we're going to talk about losing electrons, which is oxidation, and this is Leo, lose electrons, oxidize, gain electrons, reduced. So gain electrons, reduced. Leo, the lion, goes grr. That's the easiest way to remember that. So, when we talk about losing and gaining electrons, that will help you remember. There are several ways we're going to be showing this. For one, we can do dot diagrams. Sodium, 1A, 1 dot in the Lewis dot diagram. And that, let's say we're talking about chlorine, 1, 2, 3, 4, 5, 6, 7. It's in 7A. So obviously chlorine, Cl, is going to gain an electron and be reduced. Sodium is going to lose one and then resort back to that next inner level, which has 8. Both of them end up with 8. We've got our octet rule. They're both stable. So sodium oxidized, chlorine reduced. Metals have a tendency to be oxidized. Nonmetals have a tendency to be reduced. So you could show that with the dot diagram, and you should be able to show that. Probably a short answer question on the quiz. So we're going to go ahead and move on, and next we're going to talk about half reactions. Well, we just figured out that sodium was oxidized and chlorine was reduced. So in this reaction, 2Na plus Cl2 yields 2NaCl. We're going to take the oxidized part of it and make a half reaction, half of what's going on, and that would be 2Na yields 2Na plus 2 electrons. How do we know an oxidized reaction? The electrons are on the product side, the right side, and they are being lost. They're leaving. The reduction half reaction would be the chlorine, because chlorine is reduced, and we see that chlorine plus 2E minus produces 2Cl minus. Notice that the substances, the atoms, and the charges have to be balanced. We have 2 minuses here, 2 minuses there. We've got 2 plus and 2 minus for 0 here. We've got Na for 0 over there. Those are the half reactions. We take the half reactions, everything on the left drops down to the left side of the arrow, and everything on the right goes to the right. And when we do that, that gives us the net ionic equation. So we've got 2Na plus Cl2 plus 2E minus produces 2Na plus 2E minus plus 2Cl minus. that's the net ionic equation. We could cross through the two E's. They cancel because they appear on both sides. And should be able to write net ionic equations like that. Oxidation numbers. This is a big thing in this chapter. It's going to amount to about 30 or 40 points on the quiz and test. And really the rest of the stuff we do is going to deal with oxidation numbers. So you should spend a lot of time working on this. It may not take you a lot of time. It's not that difficult. If I had to give one overriding rule, I would say that most oxidation numbers are equal to the charge of the substance. Remember that charges, we do like 2 plus. Oxidation numbers, we do plus 2. So we put the plus on the left side, plus and minus on the left. Helps us, a little nuance, but it helps us separate the two. So let's look over the rules. And I'll tell you already, I tried to reflect the order of the rules that the book had so that you wouldn't be confused. Say, well, I thought that was rule 1, or I thought that was rule 4. But make no bones about it that rule number 4 is the first thing you should look at here. So if you want, just scratch through 1 and make that 4, 1. It's up to you. Number 4 is the first thing you should look at because 1A, 2A, and 3A, talking about the groups in the periodic table, the 1A group, 2A, and 3A are always going to be a plus, and then the numeric value of their Roman numeral, that's their oxidation number. So everything in group 1A going to be plus 1. Everything in group 2A, plus 2. Everything in 3A group will be 3 plus. Everything that y'all get at any rate here in Chemistry 1. So go over the rules. Oxidation number of uncombined atom is 0. That includes all of the diatomics. Cl2, 0. S, 0. If it's a single, like S with a plus, it's by itself, and there's no charge, has a 0 for oxidation number. These rules are not that hard. You need to spend time learning them. And the people that don't do well on this are the people that don't spend time learning them. Number 2, oxidation number of a monatomic ion is its charge. Ca2 plus is not an atom, it's an ion. It's a cation. So it has a 2 plus charge, going to have a plus 2 oxidation number. We always write an oxidation number above every capital letter. That would be where the oxidation number should be to show that you know that's the oxidation number, that's the correct place for it. So this is the charge, that's the oxidation number. Third rule, oxidation number of oxygen is minus 2 except when 1A, 2A, and 3A members make it be minus 1. So in other words, oxygen could be a minus 1. Let's look at some examples. Here's Na2O, sodium oxide. That's regular sodium oxide. Here is sodium peroxide, Na2O2. That would be peroxide. Per means more, like hyper means more, and it has more oxygen, so it's peroxide, more oxygen. And we'll see how this affects. So first of all, we're going to bump up again and talk about Rule 6. All of the sums of the oxidation numbers in a neutral compound are 0. That helps us find one we don't know if we know the other one. We do know this one. It's plus 1 because it's sodium. Sodium's in 1A, plus 1. And if there's 2 plus 1s, that would be plus 2. So oxygen has to be minus 2. 1 times minus 2 would be minus 2. Plus 2 minus 2 equals 0. We're good to go there. So the oxidation number for oxygen here is minus 2, which is the norm. Now we're going to see how that works with the peroxide. Sodium is in Na2 again, but we've got O2. Remember, we've got extra oxygen. So sodium is a plus 1. 2 times plus 1 is plus 2. And we need a minus 2 to be equal and opposite, but there's 2 oxygens. So we know oxygen has to be a minus 1. 2 times minus 1 is minus 2. Plus 2 minus 2 equals 0. So those are our oxidation numbers. When oxygen is in a peroxide, its oxidation number is minus 1. And we'll know that. I'll only give you peroxides with 1A, 2A, and 3A. You'll know that because 1A, 2A, and 3A force it to be a -1. All right, so looking back at the next rule, we already talked about number 4. Main rule, I would look at that first. Members of 1A, 2A, and 3A groups on the periodic table are their Roman numeral a plus and their Roman numeral values. So like +1, +2, and +3 for 1A, 2A, and 3A. Oxidation number of hydrogen is +1, except when rule number 4 and number 6 make it be -1. Here's hydrogen. Has 1 proton, 1 electron. It can lose that electron and be H+, or it can gain an electron and be H-. NaH would be an example when you see hydrogen in that second spot, except for NH3 and NH4. Those cases that really, those are the main cases you'll see that are an exception. When H is in the second slot after a metal, it's going to be a -1. Rule 6, we already talked about that. The sum of all of the oxidation numbers, when you're multiplying times the subnumber, all of that has to equal 0 on a neutral compound. And number 7, kind of the same rule. If it's a charged polyatomic ion like SO4, 2-, then we're going to drop that 2- down here, and all the work has to add up to -2. So instead of being neutral, it's got a charge. So all the numbers have to add up to that charge. Oxygen, not with 1A, 2A, 3A, so we know it's -2. 4 times -2, -8. And sulfur, there's 1 of those, so we need a +6. +6 -8 adds up to -2. And that tells us that +6 is the oxidation number for sulfur. One thing kind of neat about the polyatomic ions is that once you've done it, SO4 is always going to be +6 -2. For y'all it will be at least. So once you've done that, if you can remember that, you just plug it in right away. But whenever you have 2 polyatomic ions in a compound like NH4 to SO4, split them. Do NH4 separate and do SO4 separate like we did here, and then you can put them back together and check your results. So that would be oxidation numbers. I recommend that you do some practice on those and replay this if you need to go back through and catch things you might have missed, because oxidation numbers is going to be really important. Here's some practice assigning oxidation numbers. Something I noticed on the first printout that I did, the SO3, I made it add up to 0. It should add up to -2. Or actually, that one is SO3 sulfur trioxide. So it's right the way it is. If it were SO3 2-, that one would add up to -2, so it would be +4 -2. If it's SO3 sulfur trioxide, neutral compound, then it's going to be +6 -2. One thing that I did notice down here at the bottom, on H2O2, hydrogen peroxide, I had -1 +1, should be +1 -1. So make sure that you make those corrections. Right, so go through, do those, make sure you get some good practice on those, and you can also do the practice pages that you get online or in the classroom. So we're going to finish up by talking about the oxidation number change method for determining whether a substance is oxidized and reduced. This is important because tomorrow, the next lesson, we're going to talk about the oxidation number change method for balancing. So it's going to be, about 80% of it is going to be all this stuff, and then we're going to add 3 more steps to the end. So, first step, assign oxidation numbers. Na plus Cl2 yields 2 NaCl. We're not going to balance it yet. We're going to wait. So, we assign oxidation numbers. Element by itself, 0. Element by itself, even though it's diatomic, 0. Na and Cl, now it is a polyatomic ion, or I'm sorry, it's a ion because it has formed an ionic compound. So Na is in group 1, +1. Cl, well, if you've got 1 + 1 and all this has to add up to 0, 1 - 1 makes it add up to 0. Then, next step, you connect the substance with the numbers that increase on top. So goes up, okay? If the value goes up, it goes up on top. That's plus 1. The one that goes down, okay? So we put the one that decreases on the bottom. Chlorine goes from 0 to minus 1. Sodium goes up from 0 to plus 1. We write the value inside the parentheses. The one that's reduced is reduced. It's that easy. Chlorine went down, it's reduced. Sodium went up, it's oxidized. Remember, it went up because minus a minus is plus. So when you lose electrons, you're going to have a positive change. That would be the oxidation number change method. There are a couple of practices. It shows you another CO2 formation, oxidation reduction, and then another practice with sodium and bromide. Run through and try those practice, see how it goes, and do lots of practice on this, because the more you practice it, the better you'll get, and the better you do on your quiz, your test, and your review. Good luck.